Hi, this is John Isles and welcome to Geometer's Paradise. Today we're going to be talking about the trichotomy of numbers and the exterior angle theorem, among other things. To begin with, our first goal is to convert equality to inequality and vice versa, and finally to identify greater and lesser values from a number of different geometry equations. The trichotomy of numbers basically says this. If we have any two numbers, a and b, these two numbers exist in one of three possible relationships. First, a can be greater than b. Second, a can be equal to b. And third, a can be less than b. Of course, we call this the trichotomy. This is really useful when we start talking about proving things like proving inequalities, because one of the things we can use is something called a proof by contradiction. So if I wanted to prove that something was greater than something else, I could actually prove it by showing that it's not equal to or less than. Since the trichotomy says that we have to be greater than, equal to, or less than, by showing something is not equal to or not less than, we know that it has to be greater than. So that's the importance of this concept. We define inequality as the ability to add something to another number so that you're equal to the larger value. So 7 is greater than 5 mainly because 7 is equal to 5 plus 2. We can generalize this and say that any number x is greater than a number, is greater than y if x equals y plus some other constant value. In this slide, we note that we can convert inequality anytime we have an expression like this so that x is larger than both y and z. Then we know that 8 must be greater than 5 and 8 is greater than 3. Or if we have a segment addition, like this is a segment addition, we have a line segment AB with a point C on it so that AC plus CB is equal to AB. This means that AB is larger than either of the two pieces that make it up, which, totally makes sense. This second one here is an angle addition, same kind of deal. We've got an angle ABC with the line segment BD, kind of go through in the middle. And now we know that angle ABC is greater, is greater than either ABD or DBC. Okay, so let's think up for a moment here some geometry theorems that result in this kind of a scenario. A equals B plus C. There's the exterior angle sum theorem, for example, where the exterior angle, usually called angle 1, is equal to the sum of the two interior angles. There's complementary angles. There's supplementary angles, linear pairs, the consecutive interior angles theorem, the angle addition postulate, the segment addition postulate. There is the triangle angle sum theorem. There's the right triangle angle sum theorem. Okay, all of these things result in things being added up equal to something else, and that's the idea. Any of these can be used then to generate inequalities. For example, here's the exterior angle inequality theorem. This is EAIT as opposed to EAST. So this should say sum. Okay, so what we can do here, angle 1 is equal to angle 2 plus angle 3. This is the exterior angle sum theorem. Now, from this, we can say that angle 1 is greater than angle 2 by the definition of inequality, and also that angle 1 is greater than angle 3 by the definition of inequality. and that generates our exterior angle inequality theorem, which we abbreviate like this: exterior angle inequality theorem. And to me, this says exit. So just another fun way of remembering that there is such a theorem: exterior angle inequality theorem. We can apply the exit theorem, and indeed we do in your homework quite frequently, to find all the angles that are less than angle 1. So the goal here is to only use the exit theorem and nothing else. So you don't look at the angle 1 and say, hey, it's obtuse, it must be bigger than all the acute angles. Okay, that's not allowed. And instead we say angle 1 is greater than angle 3 and angle 4. Angle 1 is greater than angle 3. It's also greater than angle 4 by the exterior angle inequality theorem. And then we note, hey, angle 4 is bigger. See, angle 1 is bigger than 3 and 4. Well, angle 4 is bigger than 7 and 6. And that means that in turn, angle 1 is greater than angle 7, and it's greater than angle 6. We can continue to do this with any number of theorems, like the segment addition postulate, knowing that AB is equal to AC plus CB. Whoops, that should be a B. All right, that's then allowing us to say that AB is greater than AC and that AB is greater than BC. You can do it for linear pairs. Triangle angle sum theorem. The tasty follow-up. Well, just ignore this. This is about reflex angles. And the idea here is that let's back it up just a step. Let's back it up. This is a good slide, but it requires this one first. Okay, so we know that in a triangle, angle 1 plus angle 2 plus angle 3 is equal to 180 degrees. This is tasty. Now, from this, we know that 180 is greater than angle 1, that 180 is greater than angle 2, and that 180 is greater than angle 3. Okay? This effectively means that 1, 2, and 3 cannot be straight angles, and they cannot be greater than straight angles. Which leads us to this question. We defined a long time ago that a reflex angle is one whose measure is greater than 180 degrees. A reflex angle refers to this part of the circle formed by this angle. So if this is the angle, okay, its reflex is all this stuff out here. So, can any one interior angle of a triangle ever be a reflex? The answer is no, because all of the angles have to be less than 180 degrees. And then in addition, can any one angle in the exterior of a triangle ever be a reflex angle? And again, the answer is no, because an exterior angle of a triangle forms a linear pair. So x plus y is equal to 180. That means that the exterior angle has to be less than 180 degrees. So no angle in a triangle or outside of a triangle and formed from one of its edges can ever be greater than 180 degrees. This is as a result of all of these inequality type theorems.